In many velocity problems, what happens is that more than one velocity will combine to contribute to a final velocity for some object. For example, a boat may have a motor that gives it velocity, but also current that affects its velocity. An airplane, of course, also has engines, but it's going to be subject to winds. You could imagine a man walking on a cruise ship. He's walking, so he himself, his legs give him velocity, but the ship is also moving. If you think about that one, in particular, to someone standing on the shore, they're going to see the combination of how fast the ship moves as well as how fast he's walking. And they're going to judge that, perceive that to be his final velocity. Quick question for us to consider. What velocity vector describes a person running on a treadmill? Well, the answer to that is hopefully 0, because hopefully the person is running with velocity in one direction, and the treadmill is running with velocity exactly the same, but in the opposite direction. Otherwise, this person's going to end up falling off the treadmill, right? So the two velocity vectors would add up to 0. All right. This gives us a clue, actually, as to how we'll generally go about solving those velocity problems. When we add all the parts of the velocity, that gives us our final velocity. To state that a little bit more clearly, the velocity of an object relative to a stationary point is equal to the sum of the other velocity vectors. We'll use Vg to represent the velocity with respect to the stationary point. The G just stands for the ground, something that's not moving. And Vg then is the sum of however many other velocity vectors are contributing to the motion. Here's an example. A boat travels due east at 20 miles per hour relative to the water in a river with a northeast current of 4 miles per hour. Find velocity, direction, and speed relative to the shore. So let's see what's going on here. The boat itself is going due east at 20 miles per hour. So I'm going to go ahead and say due east with a magnitude of 20. This is going to be the velocity vector, and I'm going to call it VB for the boat. We also have a current going northeast at 4 miles per hour. Just says northeast, no angles, so I'm going to assume that means perfectly northeast. That would be a 45-degree angle. It's got a magnitude of 4. And so that's going to be my velocity vector, and I'll say VC for the current. All right, let's go ahead and write down actual vectors using standard position notation for the velocity of the boat and the velocity of the current. The velocity of the boat, since it's entirely due east with a magnitude of 20, must end here at 20 on the x-axis. And so it's easy to write down its vector as just 20, 0. The velocity vector for the current, I'm going to go ahead and use my v1 cos theta and v2, or v1 sine theta. Excuse me, I said that wrong. v1 is the magnitude of v cos theta, and v2 is the magnitude of v sine theta. So in this case, it would be 4 cosine 45 degrees and 4 sine 45 degrees. Since those are just unit circle values, I know the cosine and sine for 45 degrees is the square root of 2 over 2. And so I've just got 2 square root 2 and 2 square root 2. As my VC. All right. The velocity vector with respect to a stationary point on the ground, then, is just VB plus VC. Which will be 20, 0, plus 2 square root 2, 2 square root 2. And let's see, I'm going to give the final answer as a decimal. What is 2 square root 2? It's about 2.83. So I'll get 22.83, comma, 2.83. All right, I found the velocity relative to the shore. That's my VG. I was also asked for direction and speed relative to the shore. So let's finish up by giving those values. This would be still in the first quadrant, right? The x value is 22.83. The y value is 2.83. So my velocity vector looks like this. That's VG. And I could say the speed is just the magnitude of that vector. Which gives me about just about 23, actually. And the speeds in this problem were in miles per hour. And as far as the direction, I know that the tangent of theta is V2 over V1, so 2.83 over 22.83. And so if I take the inverse tangent of that, I get about 7 degrees. I can just say 7 degrees if I want to, or if I want to be really explicit in terms of the directions, that would be 7 degrees north of east. And so there's the speed and the direction that the boat will actually go when you consider how it's trying to move along with the current. All right, it's not always necessarily true that VG is the unknown. Sometimes one of the contributing velocities may be unknown. So we'll look at that in our next example. In example 6, a canoeist knows that she can paddle at a steady rate of 4 miles per hour in still water. She heads due south in a river with a current, but she actually progresses 10 degrees east of south at the rate of 3.2 miles per hour relative to the shore. Find velocity, direction, and speed of the current. Now in this case, notice that this description right here, because it says relative to the shore, that's the VG for this problem. We also have the canoeist herself. So we've got her going 4 miles per hour. And our goal is to find the unknown current. So once again, let's make a little picture of what we have. In this case, the canoeist is heading due south at 4 miles per hour. So magnitude of 4 here. And I'm going to call that VB for the boat so that I can still use VC for the current. VG is 10 degrees east of south at a rate of 3.2 miles per hour. So let's see. There's east of south by 10 degrees. And the magnitude is 3.2. And there's VG. Let's go ahead and write down some vectors for VB and VG. VB, since it's directly south, would have 0 for its x component, and I want to go with -4 to make that south rather than north. And for VG, we'll go with magnitude 3.2 times the cosine of 10 degrees, and then the 3.2 times the sine of 10 degrees. And I'm just going to get a decimal approximation for those right now. That's about 3.15. And about 0.56. And I'm sorry, I looked at those numbers and realized that can't possibly be right. And of course, I know the reason for that. You guys probably already knew. My angle here, my 10 degrees, was not with respect to the x-axis, and it must be. Clearly, that's not a correct fourth quadrant velocity vector. So I know it's not right. Maybe stop and think. Let's fix that. With respect to the positive x-axis, instead of the 10 degrees, what would I actually have to use? I'd have to come all the way around here, 270 plus 10. I'd actually have to use 280 to get this right. Sorry about that. So let's fix my velocity vector here. That didn't work out very well. We'll just put it above. 3.2 cos 280 gives me 0.56, and 3.2 sine 280 gives me -3.15. That looks a whole lot better. We've now got a small positive x value and a larger negative y value. That makes sense. All right, so I know that VG has to be the velocity of the boat plus the velocity of the current, which I don't know yet. So I'll put my VG in here. And my VB. And then the unknown VC. I'll simply want to subtract this vector over to solve for VC. So in fact, if I technically do a 0 and a +4, I will have VC. And that'll give me 0.56 and 0.85. So notice the velocity of the current is slightly to the east and slightly north. That makes sense, right? She's got to be blowing or being pushed slightly east. She was trying to go south, and she ended up east of that. And the fact that it's going slightly north is what slowed her down. She was trying to go 4 miles per hour, but she actually only progressed 3.2. So that seems reasonable for the velocity of the current. To take care of velocity, once again, we'll do a speed and direction. Speed, just the magnitude of that velocity vector. Is about 1.02. And I think this was miles per hour again. And the direction, we know that the tangent of theta is V2 over V1. So that would be 0.85 over 0.56. And I'll take the inverse tangent of that. And that's about 56.6 degrees. I think that angle is going to work out fine this time. If I think about just my v of the current for the moment, that was just a little velocity vector here in the first quadrant, a positive x and a positive y would have looked something like that. So that VG of 56.6 seems like a reasonable answer. That would be north of east. And I don't need to adjust for quadrant at all. All right, let's do one more, a three-dimensional example this time. We have a model airplane flying west at 10 miles per hour relative to the air. It encounters a horizontal crosswind blowing northeast at 5 miles per hour, and also an updraft of 3 miles per hour. Notice that just put us into the third dimension, that up. Find the velocity vector and the speed of the plane relative to the ground. So let's see what we've got going on here. Keep in mind the y-axis, positive y-axis is still north. Positive x is still east, so west is actually back here on the negative. South would be over here. And the airplane is actually flying west at 10 miles per hour. So there would be my VP for the velocity of the plane, with a magnitude of 10. Let's write that down right now. Because that's on the x-axis, the negative x-axis, I'm going to say three-dimensionally that negative 10, 0, 0 would be a good velocity vector to use. All right, next we've got the horizontal crosswind, northeast at 5 miles per hour. Perfectly northeast again tells me I should use a 45-degree angle, so we'll do that. And let's see, halfway between north and east, right here, with the positive x-axis, be careful there, Christy, there's a 45-degree angle. And let's see, it's 5 miles per hour, so a magnitude of 5. And that's the velocity of the wind. I'll call it VW. So that's going to be 5 cos 45 degrees and 5 sine 45 degrees. And let's just go straight to decimals this time. I can get exact values, but ultimately we'll probably want a decimal velocity vector. So 5 cos 45 is about 3.54. And 5 sine 45 is about the same. All right, we also have an updraft. Straight up, 3 miles per hour. So straight up is going to be right on the z-axis. And that is a magnitude of 3. And I'll call that VU for the updraft. So VU is just going to be 0, 0, 3, right up the z-axis. All right, our goal is to find velocity and speed relative to the ground. So VG is what we were trying to find here. And that's just going to be the sum of all 3 of these contributing vectors. So let's see if I add them up. Oops, and you know what? I forgot to put the 0 on this one. This was in the xy plane, so I had my x and my y, but the z value would have been 0. Let's see, what am I going to end up with? Negative 10 plus 3.54 is negative 6.46. For y, I just have that 3.54. And for z, just the 3. So there's the actual velocity vector for this model airplane. I can, of course, find its speed by taking the magnitude of that. And we'll just round that off to a couple of decimal places as well. And that comes out to about 7.95 miles per hour. Again, three-dimensionally, the only direction we'll ever give is the actual vector itself, so I wouldn't ask you for a direction in a three-dimensional case. All right, that brings us to the end of our velocity examples. We'll look at some force examples in the next video.